Our universe, vast and mysterious, has a beginning. We call it the Big Bang. It happened about 13.8 billion years ago. Before the Big Bang, there was no space, no matter, no time. Everything we know burst forth from an incredibly hot, dense state. Imagine all the universe's energy squeezed into a point smaller than an atom. That's the singularity, the starting point of the Big Bang. From this singularity, the universe expanded and cooled. As it did, stars, galaxies, and planets formed. The Big Bang is not just an explosion in space, but also the beginning of time. Time itself came into existence at that moment. As the universe expands, time flows forward. But what caused the Big Bang? What was there before? These questions remain some of the biggest mysteries in science. At the heart of the Big Bang lies the singularity. This point of infinite density and temperature defies our current understanding of physics. Our laws of nature break down at the singularity. Time, as we know it, ceases to exist at the singularity. It's impossible to say what happened before the Big Bang, because time itself didn't exist. The concept of before becomes meaningless. Think of it like the North Pole. You can't go north of the North Pole. Similarly, you can't go back in time beyond the Big Bang. It's the ultimate boundary, the beginning of everything. The singularity remains a point of intense study and speculation. Unraveling its secrets could hold the key to understanding the true nature of time and the universe's origins. For centuries, people believed time was constant and universal. Then came Albert Einstein. His theory of relativity shattered our intuitive understanding of time. Einstein showed that time is not absolute but relative. It flows differently depending on your motion and the strength of gravity. Time slows down at high speeds and in strong gravitational fields. Imagine two identical clocks, one on Earth and one on a spaceship traveling at near the speed of light. Time would pass slower on the spaceship compared to Earth. This phenomenon is called time dilation. Einstein's theory also revealed the interconnectedness of space and time. They are not separate entities, but interwoven into a single fabric called space-time. This fabric can be warped and curved by massive objects like stars and planets. Let's delve into the incredibly small world of quantum mechanics. Here, time takes on a strange and fuzzy nature. At the tiniest scales, time may not flow smoothly, but rather in discrete jumps. Planck time, an incredibly short interval, 10 to the power of minus 43 seconds, represents the smallest meaningful unit of time. It's the time it takes light to travel a Planck length, the smallest possible distance in the universe. Before Planck time, our current understanding of physics breaks down. We need a theory of quantum gravity to describe the universe at this extreme scale. Such a theory would unify quantum mechanics and general relativity. Understanding Planck time could shed light on the nature of time at the quantum level and potentially reveal new insights into the Big Bang itself. Section 5. Hawking's imaginary time, a daring hypothesis. Stephen Hawking, a renowned physicist, proposed a fascinating concept called imaginary time. It's a mathematical tool used to describe the universe's state before the Big Bang. In imaginary time, there's no distinction between space and time. The universe becomes a four-dimensional sphere with no beginning or end. Imaginary time helps to eliminate the singularity problem. Think of a globe. It has no beginning or end, just like the universe in imaginary time. The Big Bang becomes like the South Pole, a point on the sphere but not a true beginning. Imaginary time is a theoretical concept, but it offers a new way to think about the universe's origin and the nature of time itself. Section 6. Arrows of time, pointing towards the future. We experience time as flowing in one direction, from the past to the future. This directionality is called the arrow of time. But why does time have an arrow? There are different arrows of time, each pointing to the same direction. The thermodynamic arrow of time is based on the second law of thermodynamics, which states that entropy, or disorder, always increases. Imagine a cup of coffee spilling. The coffee molecules spread out, increasing disorder. This process is irreversible. We never see coffee spontaneously gathering itself back into the cup. The cosmological arrow of time points in the direction of the universe's expansion. As the universe expands, time flows forward. Section 7. Time warps, the curious case of black holes. Black holes are regions of space-time where gravity is so strong that nothing, not even light, can escape. They are formed when massive stars collapse at the end of their lives. Near a black hole, time behaves in extreme ways. Time slows down dramatically as you approach the event horizon, the point of no return. If you were to observe a clock falling into a black hole, you would see it tick slower and slower until it appears to stop at the event horizon. From the perspective of an object falling into a black hole, time would continue to flow normally. However, the object would be stretched and compressed by the intense gravitational forces, a phenomenon known as spaghettification. Section 8. Cyclic universes, a dance of creation and destruction. What if the Big Bang wasn't the beginning of everything? Some theories propose that the universe goes through cycles of expansion, known as Big Bangs, and contractions, called Big Crunches. In a cyclic universe, time would not have a beginning or end. It would be infinite, flowing through endless cycles of creation and destruction. Each cycle could have different properties and laws of physics. Cyclic universe models provide an alternative to the traditional linear view of time. They offer a captivating vision of a universe eternally reborn from its own ashes. Section 9. Quantum time, a fuzzy and uncertain world. In the realm of quantum mechanics, time becomes a slippery concept. The Heisenberg uncertainty principle states that you cannot precisely know both the position and momentum of a particle. This uncertainty extends to time and energy. The more precisely you measure the energy of a system, the less certain you are about the time interval over which it possesses that energy. Quantum mechanics suggests that time might not be continuous but rather quantized, meaning it exists in discrete packets. This idea remains speculative, but could have profound implications for our understanding of time. Section 10. Philosophical puzzles, unraveling the nature of time. Time has captivated philosophers for centuries. Is time real or an illusion? Is it fundamental or emergent? These questions continue to spark debate and contemplation. Some philosophers, like Immanuel Kant, argued that time is an a priori intuition, a fundamental structure of human experience. Others, like John McTaggart, proposed that time is unreal, an illusion created by our perception of change. The nature of time remains one of the most profound and enduring mysteries. It's a concept that lies at the intersection of physics, philosophy, and human experience. Conclusion time, a fundamental aspect of our universe, remains an enigma. From its explosive beginning at the Big Bang to its perplexing behavior near black holes, time continues to challenge our understanding. Whether it's Einstein's relativity, Hawking's imaginary time, or the fuzzy nature of quantum time, we are constantly refining our comprehension of this elusive concept. As we delve deeper into the cosmos, we may one day unravel the true nature of time and its profound implications for our existence.